Okay, hi, my name is Alexander Christian, and I will present you the work me and my colleagues did on multi-itinerary optimization as a cloud service, or for short, we just call it MIO. Now, the motivation behind MIO is the high demand for efficient cloud plan. Now, we have courier services, home care assistance, or even other kind of businesses. We saw, for example, that we have bicycles that are being broken and need to be collected. And in these kinds of scenarios, we have one or more vehicles and a set of locations that need to be serviced. So finding the optimal route in these cases can help reduce the operating costs of those businesses. For example, for a client that we analyzed, we noticed that using our solution would actually reduce by 15% their travel time and also use fewer vehicles. And this is an increase in productivity, and it can also help the environment by reducing the carbon footprint. To do this, we leverage our algorithms knowledge and extensive map data, and we build our solution on top of Azure Cloud Infrastructure. Now, what is MIO? It's a new API from Bing Maps, and it's aimed at automating the process of building itineraries for one or more agents, and it can span multiple days. Now, it supports service time window definitions. For example, those are business operating hours. You can have a location dwell time, and that can be the amount of time needed to spend at a specific location to perform a task. And you can also have location priorities to ensure high importance targets are serviced. And we offer a wide range of support from small requests that have just a couple of locations and a few agents. And we service that through normal synchronous calls. And we can also support up to 10 agents and 100 waypoints if you do a async call pattern. I actually have a small demo prepared for this to better understand what our service does. And let me just change to that. Okay, so in this scenario, I already did a request that's with 4 agents and 40 stops. For each agent, we have a shift start time, an end time, and for each shift, we have locations. In the right panel, you can actually see in here that we have for each agent a nice route that's being plotted on the map with the locations it needs to visit. And for each location, like I said, we have the time windows with the opening and closing time, a dwell time priority. And later down in this demo page, you can actually see the itinerary for each agent and also like a nice timeline showing where they need to be, actually showing where, when they need to be at each location. And I can actually show you for a smaller one that does a sync request with 2 agents and 5 stops that we're gonna get in a bit the result. And we can see how the points are distributed between the agents. And again, the same information. Okay, so going back to the presentation. In a second. Yeah, okay. So we should be back now. So what were the challenges we encountered when we created MIO? Well, first of all, we needed a cloud service that could scale robustly based on client demand. And second of that service needs to be able to handle locations all around the world. So that means if you have a lat long point, we need to snap them to the road network and then calculate the shortest path between all locations that you provide. Adding to that previous request is the ability to handle traffic, and that involves variances in travel time and travel distance. And finally, we need to provide a solution for an optimal route, and route optimization being on its own an NP problem. So in the next sections, we're actually going to see how we addressed a few of those issues. So first of all, The cloud service design is split in 3 individual roles, and that's done based on their specific requirements to support independent scaling based on usage. First of all, we have a service that handles the route optimization problem. Now, that's CPU intensive, but uses very little memory because we don't have any persistent data there. Secondly, we have a static distance matrix service that requires large amounts of data to be stored in memory. The CH graph for the whole world, it's around 20 gigabytes of data, and doing the computation utilizes very low CPU. And third, we have another service that's called traffic matrix, and that handles traffic dependent travel times. Now, in order to have traffic data for the whole world, that amounts to about 5 terabytes of data. So we need fast and easy access to it. So we actually use memory mapped solid state drives in this service. Now, to reach high availability for our service, we leverage the Azure infrastructure, and we have Azure traffic managers that distribute the requests between data centers. And from there on, we have Azure load balancers that select the VM on the scale set to send the request. I want to go into a few details for the traffic matrix. Now, to have accurate traffic predictions, we combine different sources for traffic, and we aggregate the input data for each of them on road segments, and we have 6 months of historical data for this. And our algorithm is designed to calculate the minimum travel time between each pair of locations in discrete 15-minute time intervals. I have another demo to actually show you what that means and how it works. So again, bear with me a bit. Okay. So I have the downtown Seattle area in here, and I'm just going to choose 5 points or so around here. And I'm going to do a request to our traffic matrix service. This is being done live, and I'm choosing a pair of points. So we have, for example, in this histogram right here in the right panel, we have the variance in traffic actually in time and distance from 3 to 1. Now, for each point that you see in here, this is a 15-minute discrete interval, and we have the minimum travel time between pair 3 and 1. So you can see that we start, for example, with a minimum travel time of 37 minutes. You probably have a small rush hour in here to start, and because this is done at the current time, so it's about 5 p.m. And it's gonna go down as we go in time, and then we have another spike in here, and this is probably in the morning or just during the day, and during the night we have a low dip in travel time. You can actually see also in here that we have different routes that we pick between these 2 points to get the minimum travel time, and this is done for each pair of points. Now, going back again to the presentation. With the travel time matrix is computed, the next problem that our MIO service needs to tackle is the technician routing problem. Now, the challenge here is to schedule a set of agents to visit a set of points at most once. And while doing this, the agent can dwell there for some time. That means perform the task that he needs to do there. And this needs to happen within the time window associated with that point. Now, the objective is to visit as many places as possible within the time intervals that the shifts that the agents have. And while doing this, we also want to minimize either the travel time or the travel distance. So to do this, there are at least 2 possibilities for this kind of problems. First of all, is fitting the problem to a linear integrated programming solver like Groby, for example. But we tried this, And you can actually see in the results that we published in the paper that this is not a solution for large problems. So for larger data sets, using an integral programming solution, it's orders of magnitude slower than our approach. Now, the other option to do is use a heuristic. And that's the way, the path we went through, and we're actually going to compare it compare our solution to another popular candidate. The algorithm behind our solution is based on a popular meta-heuristic, which is used with success in problems like this, and it's called the LNS. Now, for this, we have a local search component that's composed of pairs of repair and destroy methods, and a declaration. We choose a pair of repair and destroy methods, and that's done based on the behavior that had in previous iterations. Now, the destroy method modifies the current solution that we have to the point that it could actually make it unfeasible. And after that, the repair method comes in and modifies the solution again with the guarantee of making it feasible again. The result that we get out of that, we check if it's better than our best solution, and we update accordingly. Now, if not, based on an exponential simulated annealing framework, we either accept the result or not. Finally, we need to update the weights of the repair and destroy methods, and the algorithm terminates either on a time limit constraint, and that's determined on the size of the problem, or if we detect that there's no change in a few thousand iterations. I have actually a small demo that should run in here that's showing how LNS actually evolves over iterations. And we can actually see how the solution updates, and down there in the lower panel, it's outputting information about the current temperature, the objective. And you can actually see when this is going to run again that we very quickly reach almost good solution, and that's done like a few hundred iterations, and then we run a little bit more and we get something very good. Now, we compared our LNS implementation, like I said, with another popular solution, heuristic, and that's LKH, Linking and Heugman. This is used in TSP problems, and it's a state-of-the-art heuristic. We started our comparison on a known data set used in TSP algorithm testing. So both the Duma and the Silva data set assume that you have symmetric and static travel times. And the problem sizes vary from 20 to 400. So the results show that LKH is very fast, and our LNS implementation is typically slower, but we managed to catch up in larger problem sizes. So when we computed the accuracy, it's also plotted in there. We can see that the average deviation from the optimal, because these are known data sets, it's well within our quality constraint limits. But real-life scenarios actually involve traffic, and this results in asymmetric and time-dependent travel time. So for this, we had to create our own data set, and we used a large urban area, Seattle, and in there the travel time varies a lot. So between average travel time and the maximum, you have up to 30% variability. So we compared two possible scenarios for MIO using time-dependent travel time that's obtained from our traffic matrix, and we also have MIO with free flow. So that was MIO with the SETI matrix that doesn't use any traffic information. Doing this in this scenario, you can actually yield results that violate time window constraints. This is done because an agent could arrive later to a location than the time window defined to service that location, and that is because of the real life traffic conditions. So we consider those locations to be infeasible and they need to be dropped from the itinerary. To mitigate this issue, what you can do is actually use the maximum travel time, and we also have that scenario in here in the comparison. The first important result that we got from this is that using static travel times, so that was no traffic information, free flow, locations are dropped, and in our Seattle data set, this value is on average 90%, so 90% of the initial schedule items are dropped, and it can actually grow up to 38%. The aggregated results on the chart show that if you use actual traffic information, we have an increase of 10% on average over both previous two methods. So we continue our comparison of LMS with Lincoln, but this time we use the time-dependent data set that we described before. But since Lincoln does not accommodate time-dependent travel time, we have to use the maximum travel time across a segment to go over the issues of having dropped items, and we also have to include the dwell time at the location in the actual travel time segment. So the results show that MIO is able to actually outperform Lincoln on execution time when we have asymmetric travel times, and we actually managed to schedule more items and have better results if the data set increases. You can actually see that in the blue columns. And all the experiments until now were dealing with MIO, that was using a single agent, but MIO is capable of creating schedules for multiple agents. And we wanted to know how that impacts our service. So we use the same data set and we gradually increase the number of agents. We do that by adding clones of the original one. And as expected, the number of items that you schedule also increases. But what we can see from the chart is that the runtime is not affected by the number of agents, and the dominant factor is there is actually the request size. And we can also make another interesting observation is that on the larger requests, the runtime actually decreases when you have more agents. And that's because it actually causes a reduction in the unscheduled items that you have in the pool. And that makes the problem to have a lower complexity for us. Now, the conclusions for this are that the MIO, first of all, is a Bing map service that was released worldwide and is live now. It's built on top of algorithms that can account for traffic information, and this is especially important if you have scenarios in urban areas. It achieves a sweet spot between accuracy and runtimes that are significantly better than state-of-the-art heuristics. And it's also in continuous development. So we have plans to include capacity constraints for vehicles and pickup and delivery scenarios. And we actually did that a couple of weeks ago, and it's live now. And we also want to include specialized truck routing attributes and increase the current limitations that we put on our request sizes. Thank you, and questions?